Greetings everyone. So today we are going to discuss about the new topic which is group 3A elements. So basically group 3A elements is also known as the boron family, and that is consisted of the following elements: boron, aluminum, gallium, indium, and thallium. So if you just talk about their characteristics, all of these are metals. All of these are metals. Aluminum, gallium, indium, thallium, all of these are metals. While this part, the boron, is a non-metal. Now, if you just talk about some general characteristics, very general properties, we have studied in our previous classes that when we move down from boron to thallium, when we move down the group, then the atomic size increases, due to which the metallic characteristics increases. Atomic size and metallic characteristic increase down the group. But there is one exception. One exception is there, which is that aluminum basically has the size of aluminum is greater than gallium. Size of aluminum is greater than gallium, due to which um, the um, the strength of atomic size or the metallic characteristics is in the following order, such that thallium has the most size, indium less than that, gallium, not gallium but aluminum less than that, and then we have gallium, and then we have boron. So this is the entire sequence which we need to understand. Helium, then indium, then aluminum, then gallium, then boron. Now, why does this happen? This happens, this is basically the order of metallic characters. Metallic characters. Now, why does this happen? This happens because aluminum is having d electrons in its valence shell. In its valence shell, it's having d electrons, which have a poor shielding effect. As a result of which, it causes to increase the size of atomic size of aluminum, due to which the metallic characteristics of the aluminum is ultimately increased, and that is greater than gallium, which comes out as an exception. Now let's just move on to its occurrence. What actually is their role in the environment, in our Earth? So basically, if you talk about boron first, boron is non-metal, and that is found in it comes under the category of micronutrients in plants, and is rarely used for any sort of metabolic activity in plants, and it is also found least abundant in earth as well. It is mostly found in the form of oxyborate ion combined with oxygen, and it is also found as salts of polyboric acid. Now, there are many types of boric acids which basically exist in the environment. Orthoboric acid, metaboric acid, pyroboric acid, tetraboric acid, and there are many other different types of boric acid which we are going to discuss in the upcoming part. Example of this is borax. Borax is a salt of orthoboric acid. It's a sodium salt of tetraboric acid. It's a sodium salt of tetraboric acid. This is the thing. Borax is a sodium salt of tetraboric acid, and that is an example of its occurrence in the earth. Secondly, we are having aluminum. Now, if you just talk about aluminum's role, aluminum is also is basically the most abundant element after oxygen and silicon in the Earth's crust, and that is found in the Earth's crust in rocks. It is found in rock minerals in the form of aluminosilicate ions. And it is found in the form of aluminosilicate ions, and it is the abundant element after oxygen and silicon. Alright, and then we have gallium, indium, thallium. All of these are metals which are rarely found in the Earth's crust, and they are obtained during metal processing and found in the metal processing as impurities. So it's about the occurrence. Now let's move on to the peculiar behavior of boron. There are a few points to consider. That boron is the only element in group 3a that is a non-metal, and it is the only non-metal which has less than 4 electrons in the valence shell. And third point, which is needed to be considered, as oxidation status +3 -3. Fourth point, that it does not form ionic reactions. It does not forms an ionic bond. No ionic bond is formed. The reason behind it is that uh, ionic bond is formed when there are high metallic characteristics. But boron is having a very small size and has a high nuclear charge, due to which it is unable to lose its electron to form an ionic bond. So that's the reason for it. And because of unable to losing electron, it is unable to form a stable cation. Fourth point, sorry, is done. And now fifth point, molecular addition compounds. It can form molecular addition compounds through molecular addition reactions. Through molecular addition reactions. For example, those reactions which involve a covalent bond, and those reactions which involve, which are mostly used in organic chemistry, are done with the help of, can be done with the help of boron, um, which involves molecular addition compound, molecular addition reactions. Let's move on to the next part, which is the boric acids. Sorry, before that we have borax, and then we are going to move on boric acid. Um, just keeping it aside, we have basically something to consider, which is this borax. Na2 B4O7 dot 10H2O. This is something that needs to be understood. Basically, borax, or also known as sodium tetaborite, sodium sodium salt of tetaborite, sodium tetraborate, it is naturally found in the seas of Tibet and California, in the dried seas of Tibet and California, in a deposit known as Tincal. So this is something important. And um, second thing is that borax can be obtained artificially by reacting by through an acid base reaction where we react the orthoboric acid we react the orthoboric acid with sodium carbonate or soda ash. We react hot orthoboric acid with soda ash, then the end result we will get borax, and H2O is a byproduct, plus carbon dioxide. So this is the thing. Now one thing to be considered over here is that orthoboric acid is concentrated and it is in solid form. Sodium carbonate is in solid form and orthoboric acid is concentrated. And let me just write their states as well. Of course, it's liquid. Um, all right. So here we go, aqua, and here it is, gas. Now, second method of preparation for borax is through colemanite. Colemanite is also known as calcium borate. Calcium calcium borate. Now, calcium borate, when reacts with calcium borate, when reacts with sulfur dioxide in an aqueous form, it produces borax plus calcium sulfate. It's not calcium sulfate, but it's calcium sulfite actually. Calcium sulfite and H2O. Right. So this is a thing. Now let's just move on to another portion. Let's move on to another portion, another step in which we can, um, further use it. Now, one more thing that I would like to mention over here is that whenever we are having the formation of borax with the help of polyammonite, by the way, this is the most commonly used method, common method. And an interesting fact about this is that borax is not only formed through the polyammonite, but also there is formation of a byproduct known as sodium metaborite. Sodium metaborite. Now, what is sodium metaborite? Sodium metaborite basically is an unstable acid. Now, in order to obtain more, um, in order to obtain uh, in order to obtain more borax out of this reaction, what we actually do is we cause to react we cause to pass carbon dioxide gas over sodium metaborite, due to which it gives us more borax. This is about it. All right, so it's about balancing, so we are going to do it in the later part. All right, so this is about it. And then we are having another part we are having another part um, where we have the properties of borax. So basically, borax is a white crystalline solid. It's a white crystalline solid, and that's a sparingly soluble salt. such that at 100 centigrade, if you just put that at 100 centigrade, um, um, you know at 10 centigrade, 100 gram of borax, out of 100 gram of borax, only 10 gram can be dissolved. But at 100 centigrade, out of 100 gram of borax, 99.3 gram can be dissolved in water. So basically, it's sparingly soluble. And there's another important thing, that it exists in two forms. Number one form is decahydrate, and second form is pentahydrate. If the temperature is above 62 centigrade, then it would exist at pentahydrate form, and below 62 centigrade it exists in decahydrate or the stable form. So 62 basically is the transition temperature. And one important thing, that pentahydrate is tetrahedral in shape. Sorry, it's not tetrahedral. This one is tetrahedral. This is tetrahedral, and this is octahedral. All right, and after that we have its reactions, such that when it reacts, when borax when borax reacts with borax reacts with sulfuric acid, a concentrated sulfuric acid, it gives us boric acid. Plus sodium carbonate. And when borax is borax basically, when it is reacted, when borax is hydrolyzed, it forms a strong alkali and a weak base. And borax is hydrolyzed to form sodium hydroxide and orthoboric acid. This is about it. And this hydrolysis can be prevented in the presence of glycerine. This is an important point as well. And then another important thing is when borax is fused. When borax is fused, it first converts into a white porous mass, and then gradually it converts into sodium metaborite. Oops, sodium metaborite and boric anhydrite. Boric anhydrite. Now, boric anhydrite. Sodium metaboride and boric anhydride, and that basically when it is now when this basically appears as glassy a glassy mass. This glassy mass, when it is put when a metallic oxide is put in this glassy mass, then this glassy mass produces a glow, a colorful bead, depending on the color of the transition metal of the metallic oxide, and that basically serves as a basis for borax bead test. So what's a boric bead test? When we take a fused borax, it forms sodium metaboride and boric anhydride, in which we put metallic oxide, and when we put the metallic oxide into the mixture of sodium metaboride and boric anhydride, the reaction causes to create a characteristic color of that particular metal atom, which is used to recognize the type of metal as well as the presence of metal um, in a metallic oxide, which is recognized with the help of borax bead test, and it is a qualitative exam. It is a qualitative experiment. Now, there's another important point that when borax hydrolysis, when borax is not hydrolyzed, but it would be better to say it as ionized. When borax is ionized, it forms sodium ions and borate ions. These borate ions further react. These borate ions further react These borate ions further react with water to produce boric acid and OH ions. All right. And then there is another important thing, that when borax when borax reacts with aluminum chloride, when the mixture of borax and aluminum chloride is fused, then it produces boron nitride as the main product. This nitric acid as well. Sorry to say, but it's not this. It is ammonium chloride. When ammonium chloride reacts with borax, it produces boron nitride plus boric anhydride plus H2O plus sodium chloride. This is an important reaction. And the uses of borax is such that it is used for metallurgy, such that it is used for welding purposes. The welding gas is basically borax in metallurgy. It is used as a flux in metallurgy, flux for welding. It is used for softening of water. Softening of water. Softening of water, metallurgy. It is used for testing metallic oxide using borax bead test, as previously told. Also, it is used for it is used in leather industry. It is used in paints, ceramics, medicines, etc. And it is also used in and it is also used in washing powders. These are certain uses: metallurgy, softening of water, borax bead test, leather industry, paint, ceramics, medicines, and washing powders. So that's all about borax. Now let's come to the second part, which is boric acid. Now boric acid are of four major types. Number one, boric acid is orthoboric acid. This is the one which is most stable boric acid and of most importance. So we are going to study this in detail. H3BO3. H3BO3. And then we have the metaboric acid, which we have also studied previously. Metaboric acid. So metaboric acid. And then we have the pyroboric acid, which is this, H6B4O9. And then we have tetraboric acid, which is H2B4O7. So these are all of the boric acids. Now out of these are unstable forms which convert into orthoboric acid. An interesting fact is that whenever we are going to basically heat orthoboric acid is the most stable form. When we are going to provide heat to orthoboric acid up to 100 centigrade, it will convert into metaboric acid. And when you're going to provide heat to metaboric acid up to 140 centigrade, it's going to create tetraboric acid. And when tetraboric acid is heated to an infinite amount of heat, it is going to create boric anhydride. So this is the entire thing about it. Now let's just understand how can we prepare uh, orthoboric acid. Preparation of orthoboric acid. Preparation of orthoboric. So it is important to understand alright, there might be some problem. Alright. So preparation of orthoboric acid. First type of preparation is the one which we have already done. Basically, when we are going to use borax, when we are going to react borax alright, when you're going to use borax, uh, when we basically react borax with concentrated H2SO4, it gives us it gives us it gives us H3BO3 and sodium carbonate. And second method of preparation of boric acid is through second method of preparation of boric acid from colemanite, such that we basically take colemanite and then we add sulfur dioxide to it, so which we can prepare coleman. We can prepare orthoboric acid. We take colemanite and then we are going to add sulfur dioxide in it and boil it in water. Then at that point we are going to get orthoboric acid plus calcium sulfate, calcium sulfide. So these are the methods of preparation. Now let's move on to the next part, which is its properties. Properties. What are the properties of orthoboric acid. One property is pretty clear that we can use orthoboric acid with sulfuric acid to produce borax. Borax production. Second property is that it can react with it can react with ethyl alcohol to produce ethyl borate. Plus 3H2O. And third thing is that it is a weak acid. It is a weak acid and that ionizes to form protons plus BO3 ions. And number fourth point which needs to be considered is that number third thing which sorry fourth thing which we need to be considered is that it is a weak acid due to which it does not give the methyl orange test. It does not give the test on methyl orange, but it does give a test on litmus paper from blue to red. Litmus blue to red. And another important thing is that since it is a weak acid, it cannot be used for titration, but we can add glycerol for you know having it used for titration with sodium hydroxide, and alongside that we can also have phenolphthalein as an indicator. Acha. And then we have uh, glycerol. We have got its weak acidic characteristics, and another important thing is that it is it partially reacts with sodium hydroxide or caustic soda to form borax. But that reaction is pretty limited and that's partial. After that, we have aluminum. If we just talk about the characteristics of aluminum, uh, aluminum basically is having metallic characteristics that are pretty huge. And another important fact about it is that aluminum, when reacts, whenever aluminum reacts with halogens or let's say oxygen, then it halogens oxygen, it produces amphoteric substances. It produces amphoteric oxides. So this is an important fact. Also, another important fact: boron oxide is also amphoteric. Boron oxide and aluminum oxide produce amphoteric oxides, while indium, gallium, thallium produce acetic oxides. This is an important thing. All right, and then we have, yes, and then we are going to study their reactions. So whenever aluminum is exposed to air, an aluminum is exposed to air, it basically creates a layer of aluminum oxide on its surface, a coating of aluminum oxide on its surface, due to which it is unable to react with nitric acid. Now, basically, if we just heat aluminum at a temperature as high as 300 centigrade, then that coating can be removed, and then aluminum in air can react with oxygen to form aluminum oxide, and can react with nitrogen to form aluminum nitride. And another important thing, that needs to be considered over here is that aluminum reacts with halogens to form amphoteric halogens. Aluminum chloride, aluminum reacts with fluoride to form amphoteric. And aluminum also reacts with hydrogen to form aluminum hydride, depending on oops, aluminum anhydride, aluminum hydride, right? And then we are going to have another important thing is about its uses. So basically, when it comes to aluminum, aluminum is very light. It is very light. It is around 3 times less dense than iron, due to which it is used for making ships and other structures. And when it comes to its reaction with acids, it reacts fast with concentrated acids and reacts slow with dilute acids. It does not react with dilute sulfuric acid, but reacts with concentrated sulfuric acid. Also, it does not react with nitric acid. That is the reason we use the nitric acid tankers. Nitric acid tankers are made up of aluminum, and it is also used as a kitchen foil. It is non-magnetic, so it is used for navigational equipments. It is non-toxic, so it is used in food products. It is a good conductor of electricity, a good conductor of electricity and heat, and because of this reason, it is used for making wires as well. It is a good re- reflector of radiant energy, good reflector of radiant energy. It is a good reflector of radiant energy, and it is also used in because of this reason, it is used in making of cans and bottles, aluminum cans and bottles, because it prevents the drink from being overheated, and it can react. It is generally inert, but it can react with certain acids. So this is all about it. So this is all about this video. Hopefully you enjoyed it, and hopefully we'll come again with the next topic, which is group 4 element.